So today's lesson I'm going to go over specifically potential energy, gravitational potential energy, and kinetic energy, and the equations that we can use to actually calculate them. Okay, so with potential energy, first, potential energy is energy that's there. I like to think of it as stored energy. So, for example, if you wanted to take down a building, you could use chemical energy or chemical potential energy and blow it up with dynamite, or you can use a wrecking ball. A wrecking ball you will slowly raise with simple machines, right? But as you raise it, you give it potential energy, because then when you drop it, the potential energy gets converted into the energy of motion, which we call kinetic energy, and can really do damage by knocking down a building. Okay. Now, gravitational potential energy, we have some sort of reference level. So what do I mean by that? I could take this pencil and lift it, right? And I'm lifting it, say, either from the floor up to, say, 2 meters high, or from the table up 1 meter high. So it has some sort of reference level. Am I referring to the height above the table, or am I referring to the height above the floor? Okay, so depending on how high we raise something, we need to say in reference to what, right? The floor, the table, sea level, the center of the earth. Like what is it in reference to exactly? And so we always need some sort of reference level when we're talking about gravitational potential energy. Once you have your reference level, the equation that you're going to use to calculate gravitational potential energy is the object's mass that you raise times by the gravitational field that it's in, and for us on Earth, 9.8, multiplied by the height you raise it above that reference level, h, in meters. Right? Make sure everything's in SI units, so kilograms, newtons per kilograms, and meters, and then you'll get a value for energy in joules, okay, which is the SI unit for energy. Okay, so if we consider, say, a sledgehammer, the greater the height you lift it to, the more potential energy it has. Okay, some animals actually use potential energy, like this is the bearded vulture, and what it will do, it will actually pick up its food and bones, right? Lift them up to a high height and drop them, right? Drop the bones so that they crush on tops of rocks so that they're more easily for them to digest. So let's go over a couple practice problems with gravitational potential energy then. Okay, so that's our equation. We have 4 different variables there, so we're not going to be making any triangle. Question number 1. Here we have a 58 kilogram person walks down a flight of stairs. Calculate the person's gravitational potential energy at the top of the stairs, on the landing, and at ground level. So we're going to do this 3 times. So for part A, we have gravitational potential. Let's do the top first. We don't need to rearrange this equation. We're just going to substitute mgh. Now the mass of the person is 58 kilograms. Gravitational field strength is 9.8 newtons per kilogram. And our height in this case, from the ground, our ground will be our reference level, is 6 meters. So 6 meters. Okay, and we put that into our calculator, we get 3,410 joules. Now if we go to the landing, which is 3 meters, so it's halfway to the floor, we can do the same thing. Right, substitute mgh, which in this case will be 58, times again 9.8, that's not going to change unless we go far away, times by our height, this will be 3 meters. So you can probably guess if we take half the height, we're going to end up with half the energy, which is 1705 joules. And if we go all the way to the ground is at a height of 0. So if you put in a 0 for h, 0 multiplied whatever mg is, it's going to be 0. 0 multiplied by anything is 0. So the gravitational potential energy at the ground then will be 0 joules. Just pause there. Alright, question 2. So the elevation at the base of a ski hill is 350 meters above sea level. A ski lift raises a skier with a total mass of 72 kilograms to the top of the hill. If the skier's gravitational potential energy relative to the base of the hill, we always have to say relative to what? Because we have to have some reference point for what h actually is. Where are you measuring h from? To the base of the hill is now 9.2 times 10 to the 5 joules. What is the elevation at the top of the hill? Okay, so this is a lot. Let's sort of draw a picture here, because there's so much information. So we have sea level somewhere. Here's sea level. That's sea level. And then we have the base of our hill, which is somewhere up here. Let's call this the base. And then we go up our hill on a lift all the way to the top. That's our ski lift right there. Okay, now it says the elevation at the base of a ski hill is 350 meters above sea level. So I know that from here to sea level is 350 meters. Okay, we know the mass of a skier is 72 kilograms. We have mass as 72 kilograms. And if the skier's gravitational potential energy relative to the base of the hill. So what they're doing is essentially saying, let's say the base of the hill is going to be our height of 0. And so relative to the base of the hill, the gravitational potential energy becomes this much at the top of the hill. So up here, Eg is 9.2 times 10 to the 5 joules. And it says, what's the elevation at the top of the hill? So it wants to know, what's this? So that's the question. So what we're going to do is we're going to use our equation. Knowing how much energy there is relative to here, we can figure out how high the top of the hill is relative to the base. Then we can figure out the total by just adding 350 down to sea level. So let's start with trying to figure out what this is from the base to the top. So we have Eg. So we have 9.2 times 10 to the 5 joules. That's going to equal mgh. Okay, but in this case, I'm not solving for Eg. I know Eg. I'm solving for h. This is what I want to know right here. So what I can do is divide both sides by mg in order to isolate for h. So they cancel here. So we're left with h equal to this 9.2 times 10 to the 5 joules, all divided by mg, where m is 72 and g is 9.8. Okay, so when you do that, you get a height, sort of ran out of space there, but you get a height of 1304 meters. So if we know that this right here is 1304, I can figure out your total elevation, right, elevation, by simply adding this portion and this portion together. So 1304 plus 350 equals 1654 meters. All right, so next I want to talk about kinetic energy. Kinetic energy is, I've said this before, the energy due to motion. And when you take something and you drop it, right, you take potential energy, gravitational potential energy in this case, and when you drop it, it gets transformed into kinetic energy, just like our wrecking ball here when it hits the building. Now the equation to calculate kinetic energy is 1/2 mv squared. And that squared is very, very important. What that means is if you double your speed, you quadruple the amount of kinetic energy. So put in another way, if you're driving and you're going 50 kilometers per hour, if you increase your speed to 100 kilometers per hour, so if you double your speed, you quadruple the distance it will take for you to come to a stop. Okay, so that's what this equation really is telling us. Right? I have an example of it. A hammer too. The faster the hammer, right, the more kinetic energy. And the more, therefore, displacement of the nail. Right? Same thing. Right? If you double the speed of the hammer, you quadruple the distance. So let's go over a couple examples here with kinetic energy. Question number 3. It says, what is the kinetic energy of a 0.48 kilogram lawn dart traveling at a speed of 3.4 meters per second? Okay, well, here's our equation. 1/2 mv squared. You can think of 1/2 as 0.5 if you punch it into your calculator. Or you can just divide mv squared by 2. Your choice how you want to do it. Or if you have a fancy calculator with those fractions, that works too. So here we have 1/2. Our mass is 0.48 kilograms. And our speed is 3.4 meters per second. I'm just going to repeat this, but energy is a scalar quantity. So when I write v, I'm talking about speed, not velocity. We don't care about what the direction is. And also, for some reason, a lot of students will forget to keep that squared. So don't forget about the squared there, especially when you go to punch it in on your calculator afterwards. So when you do that, you should get 2.8 joules. Pause there. All right, so our last question says a softball with a mass of 0.17 kilograms, so m equals 0.17 kilograms, has a kinetic energy of 98 joules. So EK equals 98 joules. What is its velocity? So we're looking for velocity. So we're going to have to rearrange the equation this time. So our equation is EK is 1/2 mv squared. What we can first do is get rid of this 1/2. So multiply both sides of the equation by 2. If we multiply both sides by 2, well, 2 times 1/2 is just 1. And we're left with 2ek equals mv squared. Now v is being multiplied by m. So to undo that operation, we're going to divide. Take the opposite operation. We have to do that to both sides. So it disappears on our right side. And now we're left with v squared. So now the opposite operation to a square is a square root. So we take the square root of both sides. The square root of v squared is just v. And I don't know, I like putting the variable I'm solving for on the left. It's just a habit of mine. And we're left with the square root of 2 times EK, which is 98 joules, divided by mass, which is 0.17 kilograms. Plug that into our calculator, we'll get our velocity to be 34 meters per second. And if you forgot, if you want to see what that looks like in kilometers per hour, you can multiply by 3.6 and you'll get what it is in kilometers per hour, which is 122.4 kilometers per hour. So that's pretty fast.